And we don't even need to grab another OH because we've got this guy right here. So let's do that. Remember, arrow goes to the hydrogen. Nobody cares where the hydrogen goes. The hydrogen can do whatever it wants. It's too old to need a babysitter. People only care about the electrons. So we care about where the electrons go. They're the golden child. And the hydrogens, they can do whatever they want. They need no parenting. They go wherever they end up. So we do that. And we get we get that, and then we get an alcohol and a deprotonated carboxylic acid. So, yes, actually, I'm going to go ahead and reaffirm what I said about why Fischer esterification is only going to happen in with an acidic catalyst, because carboxylic acids are, well, acids. So if you put it in a base, you just deprotonate, and now you're the least reactive version of a cell, right? So going from this to this is fine. Going from this to this, not so much. So you need to make sure you're here. Wait. Yeah, Fischer esterification. You need to go up here and be an acid to go there. Yes? Yes, no, maybe? Does that make sense? Cool. So this is saponification. And we call this saponification because this is how you make soap. So in, what's that movie with the soap? Fight Club. You know, I didn't see it until college, okay? I didn't know anything about it. I just knew it was a thing, and you don't talk about Fight Club until college, like mid-college. And then I was in the room when my roommate watched it. In there at one point, the guy gives himself like a chemical burn. Like he sits there and like lets something burn him. That's lye. That's either KOH or NaOH. Actually, they're making bar soap, so it's NaOH, sodium hydroxide. Don't ask me why, I do not know. But if you use potassium hydroxide, you get liquid soap, like in a pump. And if you use sodium hydroxide, you get bar soap. Or at least you start trying to get bar soap. If you want bar soap, you use sodium hydroxide. But sometimes it can get finicky, and I don't know why we were having problems, but I don't know. I guess bar soap is harder because you actually want it to make a bar. And you can make soap out of any oil. So if you just take, yeah, that's literally all it is. It's lye and some type of triglyceride. So a triglyceride is just, if I call this whole thing, I'm gonna call it R, even though there's an R in there. If that whole thing is R, then a triglyceride, it's got something holding it together here. I don't remember what. It's probably something super simple. And you've got these guys right here. So, O, R, that going on here. So with a triglyceride, you just, for saponification, to literally make soap out of like olive oil or something, you take NaOH or KOH and you put it with oil, and you're breaking this bond 3 times, and then you made that. And R is like really long in this case, but that's why soap is the way it is, because R is super long, so you've got this long chain of nonpolar carbony stuff, right? And then you've got not just a polar end, but a charged end. So that's why soap does what it does. It's got an end that can kind of, do you guys know what a micelle is? Is that, okay, that's a biology thing. If I say phospholipid bilayer, that's like a cell membrane, right? So phospholipid bilayers have like these guys, and the little tails are in there, and that's because this is non-polar, and then the cell's on this side, but the cell is polar, or the cell's insides are polar, and then outside the cell is also polar, generally some sort of buffer that's mostly water. So this can kind of happen the same with soaps. We just have, and yeah, that's not an oxygen, that's just, this is how biology people, this is how biochemists draw molecules. They just draw like shapes and then put like a tail on it. And here you go, that's soap. So you can get oh god, this is harder to draw than I thought. Dirt. There's a negative charge on each of these. I should have drawn a circle, because that's faster. But that isn't my cell, so they form these nice little spheres where the nonpolar end is dissolving the dirt, or oil or something that's nonpolar and water isn't going to wash out, and then they all surround that, but on the outside they've got a negative charge. So now they just took dirt or oil or something that water won't wash out and made it soluble in water. That's how soap works. Also, this is why you get hard water stains from like actual soap, and why Dove doesn't leave hard water stains, because Dove and a bunch of like shampoos and other things, and even most like dishwashing soaps are detergents, which aren't exactly this. They do have a nonpolar end and like a superpolar charged end. They're just not exactly this, because these will precipitate, fall out of solution as a solid if you have calcium or calcium is the one I can think of. Magnesium, maybe? Some of those guys. And that's what soap scum is. It's just it became an insoluble salt. The more you know. All right. Okay, hydrolysis of amides in aqueous acid. So, we've got amides, and we're going to hydrolyze them. It's going to give us a carboxylic acid and an ammonium ion, because, well, I mean, is it NH4 plus is ammonium, but like, if I have that's not ammonium, right? That's not an ammonium ion, right? I'm pretty sure it's not. So I don't like what they're saying, because on these slides, sure, I mean, if we use this specific amide or any amide that's primary and you just have NH2 on the end, yes, we're going to form ammonium. But otherwise, basically, we're going to form a protonated amine. So, more mechanisms. mechanism time. Do you want to take your break 5 minutes early or 5 minutes late? Late? Okay. Glad I asked. Even if when I estimate 5 minutes, we all know that it might not be only 5 minutes, it might be a little bit more. We're still okay? Okay, cool. Okay, so we're gonna start with this guy. We've got I'm doing this. There's no good reason to make an example as the way that they have it. H2, that has a plus, and we get we're gonna protonate that first, right? Because we are in acid. So, oh, gross. Just gonna try not to draw like that. So now we've got there, you can live over there, and this can be up here. All right, so now we've got this, and this guy can resonate. Okay, this is okay. I like we are gonna draw there. Did they draw 3 whole resonance structures? Are we cool if I skip the resonance structure where the positive charge is on carbon and carbon only has 6 bonds? Cool. If you want to see that later, let me know. Let me draw it for you later. You've got R. So we're gonna do this guy would like his electrons back, and in order to accommodate that, I mean, we could do that as a step and just have a plus charge here, but you know what? To accommodate that and still have everybody have their octet, we're gonna do that, and we get that is R, bonds to R and R prime. That's not a double bond. Is that clear? That's R prime? Okay, cool. R prime. There. Okay. Now we've got a positive charge there instead of there. So we've got a bunch of resonance. And yes, I skipped the one where carbon has the positive charge, even though we're about to attack a carbon. But you know what? I don't like doing attacking the resonance form anyway. So that's good. Let's just redraw this guy in the form. Let's redraw it in this form just because this is what we're used to picking off. Okay. So we've got water, right? I know, but stop. Okay, so we've got water, and that's our nucleophile. So, electrophile. Helps you guys, that's why I pretend that I write that up there, but it also gives me a prompt for when words are hard. All right. So we're gonna attack, and And when we attack, we're trying to form a 5th bond to carbon, so we go, hey, you know what, how about you just be a single bond instead of a double bond, and then we don't have to break any bonds or kick anybody off, or anything like that. And then we have that. Yes? So yes, we're in an acidic environment. Oh, I actually want to draw it in a square like that. Nope, it doesn't matter. Okay, cool. I get to draw the way I want. So we do this, and we get our tetrahedral 4 bonds to a carbon, nice little tetrahedral boy, intermediate. And, what is, oh, okay, gotcha. Your slides are not gonna show these steps, but in my opinion, this isn't a complete mechanism if you just put the arrows and show me that this one no longer has an extra proton and a positive charge. Now this one has a positive charge and an extra proton. So we're gonna do this. We're gonna do 2 steps in one go, but we're gonna just have some OH2 and some, yeah, and then some HOH2. So I'm gonna do 2 steps here. You could probably write it out as 2 separate steps, but we're gonna do it in one. We can steal this hydrogen, right, with just a water, and these electrons are gonna go there, and that's just gonna be an OH, and it's not gonna be charged anymore, so it'll be much happier. And then what can also happen is this guy can go attack an H3O+, which we're in an acidic solution, so we've got those, but also, hey look, we just got rid of a proton, so it's almost like we're just doing a rearrangement and not actually like, we're not adding or losing anything here, we're just sort of using water as an intermediate to trade some protons. Probably not the exact same proton, but like, also who cares if it's the exact same proton, it's never the exact same, right? There. Okay, so now we have this, we've got, that, we've got that, we've got OH, and we've got OH. So we've got all this going on, yes? We're almost done. All right, we've got this, and what do we do when we've got all this? Well, what we love to do is reform, oh, you know what? These are indistinguishable, so it could be either one. So what we love to do when we've got something like this is form a double bond, or reform a double bond, and we're gonna kick this guy off. So we get N, H, A, we've got that, so we can go, hey, you know what? We could take, we could just take another water to deprotonate this, but then we've got an amide, and ammonia is basic, right? Amides are basic. They really they like to hang out as a positive charge if they're in acidic solution at all, right? Carboxylic acids, this isn't how they prefer to be in acidic solution, right? These guys, if there's acid around, they would rather just be protonated. So we can just face this the other way for convenience. And we can do that in 2 steps, or we can just do this and show it in 1 step, and we get so, on your slides, this is just going to be NH4+, but that's dumb if you're going to say amides and you're not going to specify only primary amides, then why do the worst example? I don't know. All right, so that was only 2 minutes longer than 5 minutes, which is slightly less than 50% off. Take a 5-minute break, whatever 852 plus 5 is. 9, no, that's 10 minutes. Wait, 5 or 10-minute break, I don't know. What do we do? 5-minute break, okay. Whatever 852 plus 5 is. 857.